So if you like some remarks. The first remark is that I could have written natural log of absolute y is equal to minus x squared over 2 plus c. All right? We learned last time that the antiderivative works also for the negative values. So this would work for y not equal to 0, both for positive and negative values. And you can see that that would have captured most of the rest of the solution. Namely, absolute y would be equal to a e to the minus x squared over 2 by the same reasoning as before. And then that would mean that y was equal to plus or minus a e to the minus x squared over 2, which is really just what we got. Right? Because, in fact, I didn't bother with this because actually and the reason why I'm going through this, by the way, carefully this time, is that you're going to be faced with this very frequently. The exponential function comes up all the time. And so therefore, you want to be completely comfortable dealing with it. So this time I had the positive a. Well, the negative a fits in either this way, or I can throw it in because I know that that's going to work that way. But of course, I double check to be confident. Now, this still leaves out one value. So this still leaves out. So if you like, what I have here now is a is equal to plus or minus capital A, the capital A one being the positive one. But this still leaves out one case, which is y equals 0, which is an extremely boring solution, but nevertheless a solution to this problem. If you plug in 0 here for y, you get 0. If you plug in 0 here for y, you get that these two sides are equal. Right? 0 equals 0. It's not a very interesting answer to the question, but it's still an answer. And so y equals 0 is left out. Well, that's not so surprising. That we missed that solution because in the process of carrying out these operations, I divided by y. Right? I did that right here. So that's what happens. If you're going to do various nonlinear operations, in particular if you're going to divide by something, if it happens to be 0, you're going to miss that solution, or you might have problems with that solution. But we have to live with that because we want to get ahead and we want to get the formulas for various solutions. All right, so that's the first remark that I wanted to make. And now the second one is also, well, it's almost related to what I was just discussing right here that I'm erasing. And that's the following. I could have also written log y plus c1 is equal to minus x squared over 2 plus c2, where c1 and c2 are different constants. When I'm faced with this anti-differentiation, I just taught you last time that you want to have an arbitrary constant here and there in both slots. So I perfectly well could have written this down. But notice that I can rewrite this as log y is equal to minus x squared over 2 plus c2 minus c1. I can subtract. And then if I just combine these two guys together and name them c, I have a different constant. In other words, it's superfluous and redundant to have two arbitrary constants here because they can always be combined into one. So two constants are superfluous. Can always be combined. So we just never do it this first way. It's just extra writing. It's a waste of time. There's one other subtle remark which you won't actually appreciate until you've done several problems in this direction, which is that the constant appears additive here in this first solution to the problem. But when I do this nonlinear operation of exponentiation, it now becomes a multiplicative constant. And so in general, there's a free constant somewhere in the problem, but it's not always an additive constant. It's only an additive constant right at the first step when you take the antiderivative. And then after that, when you do all your other nonlinear operations, it can turn into anything at all. So you should always expect it to be something slightly more interesting than an additive constant, although occasionally it stays an additive constant.